Okay, we're going to start with lesson 8.2.1, and you can follow along with your textbook online, or you can just follow along with the handout. If you lost your handout, please print it out from Google Classroom. This is the same thing that I gave you before we left. All right, so let's start with the first problem. To celebrate the victory of your school's championship girls ice hockey team, the student body has decided to hang a giant flag with your school's mascot on the team wall. To help design the flag, your friend Archie has created a scale version of the flag measuring 1 foot wide and 1.5 feet tall. So this is Archie's version, and this is the bigger one that is going to be hung in the gym. The student body thinks the final flag should be 3 feet tall. How wide should the enlarged flag be? So if the scale was 1 foot wide to 1.5 feet tall, now we're looking at the real one being 3 feet tall. We want to know how wide it should be. So the ratio is to compare the height, which is the tall, versus the wide. So Archie was 1.5 feet tall and 1 foot wide. And the real version needs to be 3 feet tall. So how wide should it be? Now you can cross multiply, or you can see that this is really 1.5 times 2 to get the 3. Therefore, the actual flag should be 1 times 2, which is 2 feet wide. Sorry, my writing is pretty bad. I haven't written in a while. So, part B, if Archie uses $2 worth of cloth to create his scale model, then how much will the cloth cost for the full-size flag? Well, the small one was 1 foot by 1.5 foot tall. So let's calculate the area of the small one, right? So the scale has the area of 1/2 times 1 foot times 1.5, which gives us 0.75 feet squared. Well, if that is equal to $2 worth, let's see how much the big one would cost. The big one is 3 feet by 2 foot. So using the area model, so the large flag is 1/2, 2 times 3, that would be 3 square feet. Well, how many 0.75 square feet is in 3 square feet? If you double that, you get 1.5. You double that again, you get 3. So this times 4 gives me 3 feet. So that means that we need 4 of these to make the large version. Therefore, the cost would be $2 times 4, costing $8. Okay? So how do we know that for sure? It says, carefully cut the copies of Archie's scale version to fit into a large flag. How many did it take? So you were supposed to do this, but I will do it for you. This is the large flag. This is Archie's scale version. So what we wanted to show you is that if you put his scale version down carefully without any overlap, and it's going to be hard because I don't want to glue this down, but you could probably see that it is going to fit 1, 2, 3, and 4. So if the scale version is just twice as big, because it's only 2 feet wide, if it's twice as big, these are only 1 foot wide. If it's twice as big, it's going to fit 4 copies of these. All right, so same thing here, right? It is 1.5 foot, is 1 foot wide to 2 feet wide, 1 foot wide to 2 feet wide. So it's twice as big, therefore it's going to fit 4 copies. And we were right, it's going to take 4 copies. Therefore, it's $2 times 4 to get the final cost of $8 for this large flag of 2 feet wide. All right. So now the student body is considering the size of the flag, is reconsidering the size of the flag, is now considering enlarging the flag so that it is 3 or 4 times the width of Archie's model. How much would the cloth for a similar flag that's 3 times as wide as Archie's model cost? What if the flag is 4 times as wide? Use the resource pages. All right, so first one is 3 feet. So this one's 3 feet wide. It's much, much bigger, right? This was the 2 feet version. This is the scale, which is 1, right? So if we were to turn it the right side, and I'm sorry, the copy is a little bit off, but you can probably see it's going to fit 1, 2, 3, and there's a 4th one in here. And if I put another one here, 5, so there's 4 here, right? 5, 6, 7, 8, 9. So really, please use your imagination. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 on the 3 feet. So hopefully at this time you notice a pattern that if it's 2 feet, 2 times bigger, you require 4 flags. If it is 3 times bigger, you need 9 flags. So take a wild guess. If it is 4 feet big, 4 times bigger, how many flags should we need? So let's see, 1, 2, 3, 4, right? Let's put this 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, right? So then it takes 16 for the 4 times bigger. It took 9 for the 3 times bigger. All right, so let's answer that. So if the flag was 3 times bigger, so 3 times bigger will fit 9 flags. 4 times bigger fit 16 flags. So the cost for the 3 times bigger would be $2 times 9. It will cost $18. For the 4 times bigger flag, it will be 2 times 16. It will cost us $32. All right. So now, next question. If the area of one shape is 100 times bigger than the area of a similar shape, what is the ratio of the corresponding sides, also called a linear scale factor? And if the linear scale factor is R, then how many times larger is the area of the new shape? Well, let's see. Let's look at our pattern. If the scale factor, right, we're just making one side bigger. So if the scale factor is 3, then the area was 9 times more. If the scale factor was 4, then the area was 16 times more. So as you can see, the relationship is this number squared to get that number. So if we know the area is 100, it's 100 already. Let's go backwards. What squared gives us 100? Well, then the linear scale factor is 10. So linear scale factor of 10 to get area 100 times bigger, which means if the linear scale factor is R, then the area is R squared bigger, right? Okay. All right, moving on to the next problem. So now we know the relationship of the scale factor versus the area. So scale factor is linear, so the number is A to B. If it is area, then you need to square both the ratios to be A squared to B squared. All right. Kelly's shape at right has an area of 17 millimeters squared. If she enlarges the shape with a linear scale zoom factor of 5, what will the area of the enlargement be? Well, let's see. Linear scale is 1 to 5. That means the area scale is 1 squared, which is still 1. 5 squared is now 25. So small to big for area will now be 1 to 25. So 1 to 25 is equal to the actual area of 17 for the small, and we don't know what it is for the big, right? Now, yes, we cross multiply. We get x equals 17 times 25. This missing area is exactly 425 square millimeters. All right, so you see, once you know this linear scale, you can square both factors to get the area scale. Then we use that to figure out the missing area. All right, let's see the next one. Examine the two similar shapes at the right. What is the linear scale factor? So let's answer one question at a time. Linear scale factor, we're comparing sides. It is a 10 to 40. So linear scale factor is 10 to 40, which makes it 1/4. Reduce it when you can. So now, what is the area of the smaller figure? Well, let's look at the area scale. If the linear scale is 1 to 4, the area scale is now 1 squared, 1, 4 squared, 16. So small to big will be 1 to 16. So we don't know the small, that's our x now. We know the large. So 1 to 16 is equal to x over 656. Cross multiply this, you get 656 equals 16 times x. X, the missing area, is 41 square units. Okay? All right. Now, it doesn't always work that it's always 1 to a number, 1 to a number. We lucked out with all the previous problems, so now we're going to show you something that is not 1 to a different number. We're now going to show you that the scale can be a little bit different. This rectangle ABCD is divided into 9 smaller congruent rectangles. So there's 9 of them in here. If the shaded rectangle is similar, well, is the shaded rectangle similar to ABCD? Well, the answer will be yes, because it's using its own parts, and it's 9 congruent rectangles to make up this shaded region, right? What is the ratio of the areas? Well, shaded compared to ABCD is 4, because 4 of them are shaded, to 9. There's 9 of them, right? So they are similar, and the scale is 4 to 9. If the shaded rectangle is not similar to ABCD, well, we don't need to answer that because it is already similar. Now, these are area, right? This is an area, this is an area. So if we go backwards and figure out the linear scale factor, we can figure out what number times itself to get us a 4, what number times itself to get us a 9. So with this information, the scale factor is 2 to 3. Let's take a look at the sides. Isn't it 2 for the shaded and 3 for the unshaded? So it's 2 to 3. Okay. All right. Part D. While ordering carpet for his rectangular office, Trin was told by the salesperson that a 16 by 24 piece of carpet cost $800. Trin then realized that he read his measurement wrong and that his office is actually 8 feet by 12 feet. Oh, so 16 by 24 feet. Oh, that's no problem, said the salesperson. That's half of the size. It will cost $400 instead. Is that fair? Decide what the price should be. Well, first of all, is that really half, right? 16 feet by 24, if you half this, you get 8 feet, and you half this, you get 12 feet. So it is indeed half, but that's only because it's half of each side. Does that affect our area the same way? Let's see. The original carpet that he ordered was 16 by 24. That would give us 384 square feet. The new measurement is 8 by 12. That actually gives us 96 feet. So what is the comparison? Well, 384 compared to 96 is just 4 to 1. So if the original carpet cost $400 instead, what should the new carpet cost? Oh, whoops, I read that wrong. The original carpet cost $800. See, I still make mistakes. So $800 up here. So let's see, 4 times what to get 800? Well, now X should be $200. So is it right that they're charging us $400? No, they should not. The price should be $200. All right. Okay. So now what if we don't know much? What if we have very limited information? If the side length of a hexagon triples, how does the area increase? So the side length went from 10 to 30. Even if it doesn't go from 10 to 30, you know it's triples. So it's really 1 compared to 3, right? So the scale factor, oops, not scale, sorry. So linear scale factor is 10 to 30. Again, reduce it if you can. It's 1 to 3. Therefore, how does the area increase? Well, then area scale would be 1 squared over 3 squared, 1 to 9. So the large hexagon is 9 times bigger. Okay, and that's it. That's it for today's lesson.